So we've got a circular motion problem with centrifugal force involved. So what we're interested in is when you've got a pendulum, and when it is at the lowest point of its motion, it's moving with some velocity v, and we want to know if the string breaks, right? The maximum tension that the string can withstand is 680 newtons. So this is one of these threshold problems. What we need to do is we need to find out, so when it says does the spring break, that means we need to find Ft and compare that value to 680 newtons. And if Ft is greater than 680, then the string breaks. Right? You don't plug in this into your problem. That's the real mistake that everybody makes with these kind of problems. Okay, so let's see. So at the bottom, when it's going through the lowest point in its motion, the force is acting on it. You've got tension, which points up, and you got gravity pointing down, and you have a centrifugal force that's pointing down. Now, our sign convention for circular motion is that down is positive and up is negative. So the sum of all radial forces here is going to be minus tension plus gravity plus centrifugal force is equal to 0. Because these forces, there's no radial acceleration, there's no radial motion. If you want to argue that there is centripetal acceleration, then you can always move the mv squared over to this side and call it minus mv squared over r, because the radial acceleration points inward. So it's up to you, however you want to phrase it. Either way, you get that the tension is equal to the sum of gravity plus mv squared over r. Now I know mg is 441, right? It's 45 times 9.8, and then this is 45 times v squared over r. So I know this is 441, but I need to know the second half of this so I can compare. So I need to know what the velocity of the pendulum is when it reaches that lowest point. So let's take a look. We're told that initially the pendulum, it makes an angle of 37 degrees with respect to the vertical. So remember from other pendulum problems, if you looked at those, that if this is L, then this little segment is L cosine theta from here to here. And then this little segment is the height through which it falls, and of course the entire thing is L. So we have h plus L cosine theta is equal to L, and so the height can be gotten from L minus L cosine, in this case 37 degrees, which if we plug in 3.1 for L, we get 0.624 meters for the height. So to figure out how fast it's moving when it reaches the bottom of its motion here, we've got to use work energy because the acceleration is not constant. So we have to figure out what forces are acting on the pendulum. We've got gravity, tension, and centrifugal force. So the work done by, we have to consider the work done by each of these forces. Tension does no work. Remember that in these circular motion problems, the displacement vector at any given moment is always tangential. And these force vectors, whether it's tension or centrifugal, are both radial. And so anytime you got tangential versus radial, those are right angles. So tension is radial force. It's perpendicular to the motion at any given time, so it does no work. The centrifugal force is radial. Therefore, it's perpendicular to the motion at all times, and it does no work. And gravity does plus or minus mgh. In this case, it's plus mgh because it's moving down. Okay, so according to the work-energy theorem, I have to sum the works done by all my forces, and I set it equal to the change in kinetic energy. Now we are told that the pendulum bob is initially held at rest, so the initial kinetic energy is 0, and we get the familiar solution here where gravity is the only force doing any work, that v is equal to the square root of 2gh, so that's 3.5 meters per second. So now I'm going to take that 3.5 meters per second, and I'm going to plug it right back up in here to my v squared over r. And so Ft is equal to 441 plus 45 times v squared over r is 3.95. That's 3.5 squared divided by 3.1. So that's 441 plus 178, which is about 620 newtons. And 620 is less than 680, right? Ft is less than the maximum possible value of Ft, so the string does not break. And that's the answer we were looking for with the mathematical justification.